Good morning, everyone. My name is Usman Adamu, and I will be the one to be taking the introduction to physical chemistry. I've already written the topic in the board, and we are going to begin with gases. But before we start, I would like to define what physical chemistry is. As the name implies, it's just a branch of chemistry that deals with the application of the principles of physics in understanding chemical processes. So, therefore, in a nutshell, because it's mathematically oriented, one needs the knowledge of basic mathematics, but we are going to simplify it to the best of our ability. So, gases are one of the states of matter, just like solid and liquid. A gas consists of molecules separated widely apart in empty space. The molecules are free to move throughout their container. So, mm, characteristics of gases. Among the characters or properties of gases is what? The expansibility. Gas have the ability to expand due to the pressure they exert on the walls of their container. The second is what? The first is expansibility. There is compressibility. Generally, gas molecules are very compressible in the sense that when they are confined in a vessel fitted with a piston, one can increase the pressure of the piston to reduce the volume of the gases. That is the compressibility of the gases. The ability of the gas to reduce in volume when acted upon by external pressure. That is the compressibility of the gases. And of course, the third one, there is what? The diffusibility. The diffusibility of a gas is the ability of the gas to escape from the region of high concentration to the region of low concentration. That is the diffusibility of a gas molecule. And the last one is the word pressure. Pressure, mathematically, it is defined as what? The force per unit area. Therefore, the pressure of a gas is the force exerted by that gas on the unit area, as explained by the kinetic molecular theory that what the continuous bombardment of gas molecules on the walls of their container constitutes what is known as what? Pressure. That is the pressure of the gas. It's the force exerted by the gas on a unit area. That is the pressure. If you understand this, I think we can go to some of the parameters that defines or that describes a gas. The first one is there is pressure, there is temperature, volume, and sometimes the number of moles. That is the amount. And these are the four parameters that describes a gas. They are often described as what? The state functions. We shall see them later when it comes to thermodynamics. Let's discuss the gas laws. Of course, there are several laws, or let me say, many scientists have postulated several laws to describe the behavior of gases. The first of which is the Boyle's law. Boyle's law. Of course, to save time, let me just define this mathematically. This law is stating that at constant temperature, the volume of a given mass of gas is directly proportional to volume. Sorry, is inversely proportional to volume, or the volume occupied by a gas is inversely proportional to pressure at constant temperature. That is, volume is inversely proportional to pressure at constant temperature. In removing the sign of proportionality, we are going to introduce a constant which is K. V is equals to K over P. Therefore, PV is equals to K. So, P1 V1 is equals to K. Also, P2 V2 is equals to K. P3 V3 is equals to K, and so on. P and Vn is equals to K. So, and of course, you can say what? K is equals to K. This K is equals to this K. And this K is P1 V1. The other K is P2 V2. We can say P1 V1 is equals to what? P2 V2. This is the Boyle's law. The second law is the Charles law. This law is stating that at constant pressure, the volume of a given mass of gas is directly proportional to temperature. That means volume is directly proportional to temperature, provided that pressure remains constant. So, also, in removing this sign of proportionality, we are introducing a constant which is K. V is equals to what? KT. Of course, V over T is equals to K. We can write it this way: V1 over T1 is equals to V2 over T2. That is that in summary. The next law is the Avogadro's law. Avogadro's law. Let me write this law. The law is stating that equal volume of gases at the same temperature and pressure contains the same number of molecules. As we can see, Avogadro's law is stating that equal volume of gases at the same temperature and pressure contains the same number of molecules. Meaning, for example, if we are having, let's say for example, two vessels both containing, for example, nitrogen gas N2, and all at the same temperature. Let's say for example, they are both the two vessels are at 298 Kelvin, and a pressure of 1 atm. This one also 298 Kelvin and a pressure of 1 atm. From Avogadro's law, he's saying equal volume of gases at the same temperature and pressure contains the same number of molecules. What Avogadro is trying to say is that, let's say for example, these two equal volume of gases, this is a nitrogen gas of equal volume. Let's say they are both 1 liter, 1 liter. Equal volume of gases at the same temperature and pressure. These are two vessels containing gases, equal volume of gases at the same temperature and pressure, contains the same number of molecules. So if these conditions are satisfied, equal temperature, equal pressure, equal volume, then the number of molecules contained in the both vessels will be the same. For example, if here is 6 molecules, if there are 6 molecules of nitrogen gas here, 6 molecules, or let's say 6 moles, here must also be what? 6 moles, provided that the gases are the same and they are of the same volume and at the same temperature and pressure. That is Avogadro's law. So if you understand this very well, Avogadro told us that, for example, 1 mole of any gas at a given temperature and pressure contains the same number of molecules. 1 mole of any gas at the same temperature and pressure contains the same number of molecules. So it was determined experimentally under standard conditions. That is at a temperature of 298 Kelvin, that is 25 degrees centigrade, and a pressure of 1 atm. 1 mole of a gas will occupy 1 mole of a gas will occupy 22.4 dm3. That means if you keep a gas, if you put a gas in a container at a temperature of 298 Kelvin and a pressure of 1 atm, that gas, I mean, if you put 1 mole of a gas in a container at a temperature of 298 Kelvin and a pressure of 1 atm, that 1 mole of a gas will occupy 22.4 dm2. That is what the standard volume occupied by 1 mole of a gas at STP. This leads us to what? To the ideal gas equation. Of course, but before we treat ideal gas equation, we are going to treat it proper in our when it comes to kinetic molecular theory. But let me elaborate more on ideal gas. This ideal gas is any gas that obeys the gas laws at all temperatures and pressure. That is an ideal gas. So this ideal gas equation is the combination of the three gas equation we've treated earlier. That is the Boyle's law, Charles' law, and Avogadro's law. If you could remember, the Boyle's law is stating that volume. The Boyle's law is stating that volume is inversely proportional to pressure. That is what from Boyle's law. And from Charles' law, we know that what volume is directly proportional to temperature. And from Avogadro's law, we've learned that volume is directly proportional to the number of moles. Therefore, combining these three laws, using our knowledge of variation from mathematics, we can know that volume is directly proportional to temperature, inversely proportional to pressure, and also directly proportional to number of moles. In removing this sign of proportionality, we are going to introduce a constant known as the molar gas constant R. V is equals to R Tn over P. We can rearrange this formula to give us what? PV is equals to what? nRT, where our R is equals to what? The molar gas constant, and its unit and value depend on the what? The unit and value of pressure and volume used. For example, from PV equals nRT, making R the subject of the formula, R is equals to PV over NT. So the value of this R and the unit depend on the units of pressure and volume used. Of course, we know that pressure have many units. You can express it in millimeter mercury, in ATM, in Pascal, and also in Newton per meter. So let's say, for example, if we take our pressure, if our pressure is in what? For example, ATM, our standard pressure to be what? 1 ATM. Our volume to be equals to what? 22.4 dm cube, and our N amount is always in mole for 1 mole of a gas, for example, and our temperature to be equals to 298 Kelvin. These are all standards. This is the standard pressure, standard volume, and standard temperature. Substituting in this formula, we are going to get, if we substitute these values, of course, in this formula, we are going to get a value of R to be equals to, R is equals to, our P is what? 1 times our volume is 22.4, and our, that is over 1, that is 1 mole of a gas, and a temperature of 298 times 298. We are going to get an R value of, R is equals to what? 0.0821. If you press your calculator, you are going to get this formula. Then what is the unit? Our 1 is what? ATM, or let me write it here, ATM. This one is in what? dm cube, or liter. Dm cube is the same thing as liter. Then here is what? Per mole, since it falls under the denominator. Per mole, and of course our here is temperature in Kelvin, per Kelvin. As you can see, if we use our pressure in ATM, our volume in dm cube, and temperature in Kelvin, we are going to get an R value of this. If we go the other way around, let's say, for example, if you use a pressure, for example, a pressure of, our pressure in Newton per meter. Of course, we know 1 dm cube, 1 ATM is the same thing as 101325. 101325 Newton per meter squared. And our volume, we use our volume, for example, in instead of dm cube, we just use meter cube. That is 22. on 4. Here is in dm cube. How can we convert from dm cube to meter cube? We know that dm, the prefix dm is deci. Deci is equals to what? 10 raised to the power of minus 1. That is 22.4 times 10 raised to the power of minus 1 meter cube. But because of this cube, we are going to multiply this by our power by 3 because of this cube. So therefore, here we are going to take times 10 raised to the power of what? Minus 3 meter cube. And our temperature 273 Kelvin, and our number of moles amount is equal to 1 mole. So if we substitute it same in this formula, where is it? R equals to, we know that our R is equal to PV over NC, which is equals to 101325 times what? Our volume is 22.4 times 10 raised to the power of minus 3 over our number of moles is 1 mole and times 2928. If we press calculator, we are going to get a value of R is equals to 8.314. Of course, the unit will be what? Our pressure was in Newton per meter square. Newton per meter square. Our volume is in meter cube times meter cube, and our then per mole per Kelvin. So we can further simplify this unit. If we further simplify this unit, we can see that Newton per meter square, or let me write it this way, Newton over meter square times what? Meter cube. Yeah, times per mole times per Kelvin. Though our part of interest is here there is times. We can see here that what? Meter square can go with this cube. Therefore, our unit will become Newton meter per mole per Kelvin. And of course, from our physics, Newton meter is equivalent to joules. Since from our force is equals to what? Energy is equals to what? Force times distance. Force is in what? Newton, and distance is in meter, Newton meter, and we know that the unit of energy is what? Is joules. Therefore, Newton meter is the same thing as joules. Having that in mind, we can substitute the whole of this here with joules. Therefore, our R value can be R can go 8.314 joules per mole per Kelvin. And mind you, one of the things that usually confuse students in this course is what? Playing along with units. You can finish solving a question, get your answer correctly, but the unit might fail you. So we have to be extra cautious when dealing with units. So, as I said earlier, the value of our molar gas constant depends on the unit of pressure and volume used. If you use our pressure in ATM or volume in liter or dm cube, we are going to have a an value of 0.00H21 atm per liter per mole per Kelvin. While if you use the unit of our pressure in Newton per meter squared, our volume in meter cube, we are going to have an R value of 8.314 joules per mole per Kelvin, or Newton per meter cube per, sorry, Newton per meter squared. Newton per meter squared uh, times meter cube per mole per Kelvin, something like that. So, with this, we can go to the Dalton's law of partial pressure. What Dalton is explaining in his law of partial pressure is that when you are having a mixture of gases contained in a container, so the total pressure exerted by the gases is equal to the sum of the partial pressure of the individual gases that made up that mixture. For example, if we are having something like this, let's say for example, this is hydrogen gas. Let me use another color. The markers are giving me, or just forget. Let me just write it. The law is stating that the total pressure exerted by it these markers are very bad. Of gases So, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the individual gases that made up that mixture. We can take it this way: the partial pressure of a gas is the pressure contributed by the individual gas. Let's say, for example, we are having a container or let's say a tank containing hydrogen, nitrogen, and chlorine gases, for example. So the total pressure of that mixture of those gases that the total pressure those gases are exerting on the walls of their container is equal to the pressure contributed by the nitrogen individually, uh, hydrogen individually, and chlorine individually, meaning the total pressure PT P total, that is the total pressure, is equal to what? PA plus PB plus PC plus PD plus PN. So this is the mathematical expression of this law. The total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the individual gas that made up the mixture. Let's say, for example, we have a mixture of gas A, B, C, D. So the total pressure exerted by these four gases is equal to the sum of their individual partial pressures. That is that about Dalton's law of partial pressure. And of course, from our ideal gas law, we know that the partial pressure of each individual gas is equivalent to P equals to nRT over V. Therefore, the partial pressure of A, that is PA is equal to what? NA RT over V. PB, the partial pressure of B, is equal to what? NB RT over V. And of course, PC is equal to what? NCRT over V. So, substituting these values of partial pressure into this our general formula here, we are going to have the total pressure to be equal to what? PA is NART over V. Therefore, we are going to have NART over V plus NBRT over V plus NCRT over V. Of course, we can factorize the common terms here, which are RT over V, RT over V, RT over V. They are common all through. Therefore, if we factorize them out, we are having total pressure to be equals to, we are having our total pressure to be equals to NA plus NB plus NC all multiplied by RT over V. So from here, we can see that the total number of moles of our gases, since we are having 3 gases in that container, therefore the total number of moles will be equal to NT. The total number of moles of our gas mixture will be Na plus Nb plus Nc. Therefore, we can substitute this here. Since Nt is equal to Na plus Nb plus Nc, therefore our total pressure should be equal to what? The summation of the number of moles of the gases multiplied by RT over V. That is that about Dalton's law of partial pressure. I think let's take a question on this. Pressure Kelvin. Vessel. So, what pressure is exerted by a mixture of 2 grams of hydrogen gas and 8 grams of nitrogen gas at 273 Kelvin and in 10-liter vessel? So first, let's write out our parameters. We are asked to calculate for the pressure, that is, of course, the total pressure exerted by this mixture of our gases. And from Dalton's law of partial pressure, we know that P total is equal to N total times the molar gas constant times temperature over volume. So therefore, what is our N total? Our NT is equals to Na, or let me put it this way, NH2. The number of moles of hydrogen gas contained in the vessel plus the number of moles of nitrogen gas contained in the vessel. So, we are not given the number of moles, but of course we are given the mass of each gases. And from our basic chemistry, we know that the number of moles is equal to what? Mass over molar mass. Therefore, the number of moles of H2 will be equal to what? The mass of H2, that is 2 grams over the molar mass of H2. We know that H2, the mass of hydrogen is 1, but in hydrogen there are 2 hydrogens in a single molecule. Therefore, our molar mass will be 1 times 2. The mass given here is 2 over the molar mass of hydrogen gas is 2, which is equal to what? 1 gram per mole. And of course, that of nitrogen, that is N, the number of moles of nitrogen should be equal to what? The mass of nitrogen given, that is 8 over the molar mass of nitrogen. The molar mass of nitrogen is 14, but in nitrogen molecule N2, we are having 2 atoms of nitrogen, which therefore our molar mass will become 14 times 2, which is 28. This our number of moles is going to give us I think let me press it from the calculator. 8 over 28 is going to give us 0.25, sorry, 2857 solid moles. So we've gotten our number of moles. Therefore, going back to our formula, we can get our NT. NT should be equal to what? 1 plus 0.2857, which will be NT equals to 1.2857. So substituting this into our formula, our total pressure PT is our NT, which is 1.2857 times our molar gas constant, which is, yes, Matthew, we know our molar gas constant has 2 values. Our R is equal to 0.0821 atm liter per mole per Kelvin, and our R is equal to 8.314 joules per mole per Kelvin. So therefore, to know which of the R to use, you can use any of the R, but that will affect your unit of pressure. If you want our pressure to be in ATM, we are going to use this. If you want our pressure to be in Newton per meter square, we are going to use the second one. So now we want our answer to be in ATM. So therefore, we are using the first one. Our R is 0.0821 times, of course, our temperature. From our equation, our temperature is 273 from our question. 273 Kelvin over what? Of course, our volume. Our volume is 10 liter. That is 10 dm over 10. Our total pressure PT should be equals to 2.888 atm. You can try it. So with this, you can go to the ground law of diffusion. This Graham's law of diffusion is stating that the rate of diffusion of a gas molecule is directly proportional and is inversely proportional to the square root of its density or relative molecular mass. Mathematically, you can state this law as, since the rate of diffusion of a gas molecule is inversely proportional to the square root of intensity. That means, let's, for example, the rate of diffusion is R. R is inversely proportional to the square root of the molar mass of that gas. That is, let's say, for example, R1 and R2. R2 is also directly inversely proportional to the less M1, M2. So, if you all, this implies that our R1 is equals to K over, let's say for example our constant is 1, let's leave it 1 over. That means if our K, since it's constant, it can take any number, let's assume it is 1. So in this second one also, R2 is equals to 1 over root of what? M2. That is what this implies. So dividing R1 by R2, R1 over R and R1 over R2 is equals to what? 1 over root of M1 over 1 over root of M2. If we simplify this, we are going to get something like this. R1 over R2 is equals to the root, or let me take it step by step, root of M2 over root of M1. Of course, if you use our sword, we can extend this square root to be R1 over R2 is equals to the root of M2 over M1. This is Ground's law of diffusion. So, one might like to ask, what is this rate of diffusion? Normally, if you use, if we hear anything rate means the time taken for something to occur. That is the rate of something. So the rate of diffusion is time taken for a gas to diffuse, to escape. The time taken for a gas to move from the region of higher concentration to the region of lower concentration. And mathematically, the rate of diffusion is equals to what? The volume of the gas. The volume of the gas over what? Time taken. Time taken. Let's solve the equation to understand this better. So, uh, let's take this question. 50 milliliter of a gas effuses through a pinhole. 50 milliliter of a gas effuses through a pinhole in 146 seconds. The same volume of carbon dioxide under identical conditions effuses in 115 seconds. Calculate the molecular mass of the gas. Of course, 50 ml of a gas, which we don't know that gas, effuses in 146 seconds. So, solution. 50 ml of a gas effuses through a pinhole in 146 seconds. We don't know that. Let the gas, since we don't know which gas it is, let the gas be. You can Just assume any arbitrary alphabet or number or anything or any symbol. Let the gas be, for example, Y. Since we don't know that gas effuses through a pinhole in 146 seconds. The same volume of carbon dioxide under identical condition effuses in 115 seconds. Calculate the molecular mass of the gas. So, using our ground law of diffusion, our R1, or let me say the rate of diffusion of this unknown gas, R1, the rate at which this unknown gas effuses over what? R CO2, the rate at which carbon dioxide effuses is equals to what? The square root of what? The molecular mass of carbon dioxide CO2 over what? My. That is the molecular mass of our unknown gas. Therefore, but looking at the question, we are not given the rates. We are not given the rate at which our unknown gas effuses and the rate at which carbon dioxide effuses, but we are given the what? Their volume and their time taken to effuse. So, from the equation we established earlier, we said our rate Ry is equals to the volume of y over what? Time taken for y to effuse. Therefore, let's come back here. Yes. From our question, the volume of y, we are told that y is 50 mils. And the time it takes to effuse is 146 seconds. 50 mil of gas, a gas which we assume to be y, effuses through a pinhole in 146 seconds. Therefore, we have these parameters there in the question. Therefore, the rate of the effusion of y is equals to what? The volume, which is equals to 50 over what? 146, which will give us 0.3425. 0.3425. That is milliliter per what? Second. Per second. While the rate of diffusion of carbon dioxide, we are told that the same volume of CO2 under identical condition with the gas Y, the same volume, that is, they are having the same volume with the what? With the gas Y of CO2 under identical conditions effuses in 115 seconds. Therefore, our RCO2 should be equal to what? The volume of CO2 over time taken for CO2 to effuse. We are told that it's the same volume with the gas Y, therefore it should be what? 50 over, what is the time taken? 115. 115 seconds. 115. So, the rate of diffusion of CO2 should be equal to 50 over 115. We are going to have 50, 115, 0.4348. That is milliliter per second also. So that is not what we are looking for. We are also calculate for the what? For the molecular mass of our gas Y. So from this formula we've already written. Now we've calculated our rate of effusion of Y and rate of effusion of CO2. So we are going to substitute this into our formula. Our rate of effusion of Y, we calculate it to be 0.3425. 0.3425 over that of CO2, 0.4348 is equal to what? The square root of the molecular mass of carbon dioxide. What is the molar mass of carbon dioxide? We know carbon dioxide. Carbon is what? CO2. Carbon is 12. Oxygen is 16. 16 times 2. If you calculate it, it is going to give us, I think it's 44. But let me calculate it. 16 times 2 plus 12. That is 44. So the molecular mass of carbon dioxide is 44. 44 over that the molecular mass of our unknown gas, which we are asked to calculate, over my. Of course, if we square both sides, this is going to go with this. I'm sorry, let's clean. Where is the duster? Let's clean this, please. We are going to have something like this. The whole of this inside the bracket, that is 0.3425 over 0.4348. We are going to have 0.7877 all squared is equals to 44 over my. From here we can cross multiply 0.77 or 7877 squared is equal to what? 0.62047 my is equal to what? 44. Dividing both sides by the coefficient of my, 0.62047, 0.62047. So of course this will go with this. Our my should be equals to what? 44 divided by 0.62047. 70.9. 70.9. And since it is what? Molecular mass. We know the unit of molecular mass is what? Gram per mole. That is our final answer. That is our final answer. So, with this, I think we are done with the gas laws. We are going to kinetic molecular theory, and I think we shall continue with that in our next class. We are going to do the kinetic molecular theory. If you're having any question, you can post it down in the comment section. Thank you.